Welcome to today's deep dive. Uh, right now, the most advanced AI coders in the world are fundamentally
They
cheating.
really are.
Yeah. I mean, when you sit down, type a prompt into your favorite tool and just watch it spit out what looks like absolutely flawless Python, you're probably picturing this solitary, hyperlogical
Right,
genius.
like a super brain just crunching the logic.
Exactly. But the truth is, the entire software industry might be relying on a massive crutch right now. These cutting edge models aren't actually coding geniuses. They've just become, well, incredibly skilled at looking at the answer key.
It is a pretty controversial take, I know, but it gets right to the heart of a major blind spot in artificial intelligence today.
For sure.
We've built these evaluation systems to make ourselves feel confident in the models, but in the process, we might actually be stunting their actual reasoning abilities.
And that tension is exactly what we are exploring today. We are looking at a really fascinating piece of state-of-the-art research from a team at WSO2. The paper is titled DryRUN on the role of public tests in LLM-driven code generation. It's a great paper.
It really is. So our mission today is to figure out what happens if you rip that answer key right out of the AI's hands. Does taking away the crutch force the AI to become smarter? And, if you are relying on these tools to build software, or you're just trying to understand where the technology is going, what does this mean for the future of how we write code?
To really appreciate the scope of what the DryUN paper is proposing, we have to talk about the water we are currently swimming in.
Right. Set the stage for us.
So, modern AI models are undeniably powerful at generating text that looks like functional code. But the way we evaluate them and the way the top-tier automated coding frameworks refine that code relies heavily on something called public test cases.
Okay, and for anyone listening who hasn't worked in quality assurance, a public test case is essentially just a human-provided sample, right?
Exactly, it's an input coupled with the exact output you expect to see.
Like giving the AI a simple math problem. If the input is 2 plus 2, the output has to be 4. That is the basic idea. But the frameworks currently dominating the leaderboard systems you might have actually heard of, like CodeSim or AlphaCodium, they don't just use those test cases as a final check at the end of the process.
They don't.
No, they exploit them. They weave those human-authored examples into the very fabric of how the AI reasons through the problem.
Wait, so I feel like if I am taking a test and I have the rubric sitting right on my desk, my entire strategy shifts to just matching the rubric. Is that what the models are doing?
You're hitting on the core issue there, yes.
Yeah.
The current frameworks operate in two highly dependent phases. Before the AI even drafts a single line of code, the system forces the model to look at the human-provided public tests.
Huh.
It anchors its logic to those specific examples. It's almost like it's calibrating its brain to solve only the examples it can actually see.
Wow.
And then, once it drafts the code, we enter the post-generation phase. The framework takes that AI-written code and runs it in an external execution sandbox against those exact tests.
Just to make sure we are all on the same page here, an execution sandbox is basically a safe, isolated, virtual environment where the code can be compiled and run for real, right?
Yes, exactly. It's a live environment. If the code fails in that sandbox, the compiler spits out an error log, and the framework feeds that exact failed input and the error message back to the AI.
Isn't saying try again.
Right, here's what you got wrong, fix it.
On the surface, I mean, that sounds like a great system. It's basically an automated version of human developer writing code, running it, getting an error, and fixing it. So why is the paper calling this a flawed paradigm?
Because it creates a severe disconnect from the messy reality of actual software engineering.
How so?
Think about how you build software in the real world. You're usually trying to solve a novel problem. Ground truth input-output examples rarely exist before you actually write the code.
That's true.
You don't have a magical oracle that has already mapped out every possible output for every possible edge case.
And let's be honest, even when human developers do bother to write public tests for these AI benchmarks, they're usually just covering the happy path.
Oh, absolutely.
They provide the most basic, straightforward examples because, writing complex, convoluted edge cases takes a ton of time.
That is the critical vulnerability in the current system.
Yeah.
The AI is anchoring its entire logical architecture to these really simplistic, human-authored examples.
Okay, so if I can throw an analogy at this.
Go for it.
It is like giving a student the easiest possible flashcards to study for a final exam. The student memorizes those flashcards, aces the practice quiz, and feels incredibly smart.
Right.
But then they sit down for the actual final exam, the questions are completely different, and they fail spectacularly because they never actually learned the underlying material. They just memorized the easy path.
That captures the dynamic perfectly.
Yeah.
The researchers even formalized a term for this specific phenomenon. They call it the overconfidence gap.
The overconfidence gap, I like that.
Yeah, because the AI models rely so heavily on these trivial public tests for their external feedback, they pass them almost immediately. The execution sandbox gives them a green check mark, and the automated framework accepts the solution.
But it's a false positive, essentially.
Exactly. The model becomes algorithmically overconfident in a solution that is fundamentally fragile.
Which is terrifying if you are an enterprise company using AI to write your back-end logic. The AI tells you the code is perfect because it passed the easy tests, you deploy it, and then it instantly breaks when a real customer does something unexpected.
That is the real danger of the overconfidence gap. The model passes the visible public tests, but completely crashes on the hidden, private test suites that are designed to check those complex real-world edge cases.
Wow.
We basically train these highly advanced neural networks to be lazy. We give them the easy flashcards, they optimize for those, and they just stop utilizing their deeper critical thinking skills.
So the industry has built this massive, expensive feedback loop that actually encourages shallow reasoning.
Unfortunately, yes.
That completely sets the stage for what the WSO2 researchers wanted to test. They essentially asked, what happens if we take the training wheels completely off?
Right. They introduce a framework called DryRUN, which stands for Debugging and Refinement Under Non-Execution.
Non-execution, okay.
Yeah, the defining characteristic of DryRUN is its strict zero-example constraint.
Which means they didn't just casually ask the AI to ignore the examples, right? They actively scrubbed the data set.
They did. They used a widely recognized benchmark called Live Code Bench. It is essentially a constantly updating gauntlet of new programming tests designed to evaluate AI.
Standard stuff.
Right, but before they let the model see the problems, the researchers used another LLM to scrape away every single concrete sample example.
Oh, wow.
They stripped the prompts down so absolutely nothing was left except the raw, standardized text descriptions of the input and output formats.
They plunged the model into complete darkness,
Yeah.
no human examples to look at, and no execution sandbox to actually run the code and check for errors.
Total darkness.
I have to push back here, though, because my brain is really struggling with the logistics of this. If you take away the compiler, how does the AI have any idea if its code works?
It's a fair question.
I mean, if I took away a live compiler from a human software engineer, they would probably just quit. Is the AI just hallucinating its own success?
It is a completely natural reaction to be skeptical of this, but the elegance of the DryRUN algorithm is that it shifts the burden of verification entirely inward.
Inward how?
It forces the model to synthesize its own reality. Instead of relying on external tools, it has to use its own reasoning capacity. The researchers constructed a very specific journey for the model to follow, and it starts with a strict planning phase.
How do you force an AI to plan? Because, I mean, in my experience, the moment you give an AI a coding prompt, it eagerly starts spitting out lines of Python before it even knows what it's building.
That impulsive behavior is exactly what they had to suppress. In the initial phase, the model is explicitly instructed to write a step-by-step implementation plan based solely on the raw problem description. No code allowed. But the crucial part is that it autonomously refines this written blueprint. It reviews its own plan, looks for missing edge cases, and rewrites the blueprint to be more robust.
So it's double-checking its own logic.
Exactly. And it loops through this self-critique exactly twice before moving on.
So it is laying down the logic architecture first. It's building the foundation before it gets distracted by syntax errors or, missing commas.
Exactly. Which prepares it for the second and arguably most fascinating part of the journey.
Which is?
Mental simulation.
Okay, mental simulation.
The model finally generates its initial draft of the code based on the refined blueprint. But as you pointed out earlier, it has no compiler. It has no sandbox to run it in.
Right.
So to test the code, the model autonomously invents its own valid, non-trivial input based on the parameters of the problem.
It creates its own flashcard?
It creates its own flashcard, but one that is actually useful. And then it simulates the execution of the code line by line in its own mind.
In its mind. That's wild.
It tracks the changing states of the variables, it mentally loops through arrays, and it calculates the final output purely through language-based reasoning.
Wow.
By forcing itself to trace this execution path, it exposes its own hidden logical flaws. It takes those discoveries, updates its blueprint, and regenerates the code. And it goes through this mental simulation loop twice.
That is incredibly impressive. It is essentially running a virtual machine inside its own neural network.
Basically, yes.
But I do see a practical issue here. If I sit at a whiteboard and rewrite a complex algorithm twice from memory without a compiler to yell at me about typos, I am going to end up with missing brackets and weird syntax errors.
Yeah.
I mean, mental simulation is great for logic, but it's terrible for syntax, right?
The researchers anticipated that exact problem. Regenerating code purely from abstract mental tracing does tend to introduce stylistic anomalies or, syntax drift.
Makes sense.
That is why the final step of the journey is a polish phase. The model takes its finalized, battle-tested blueprint and does a final side-by-side review with the latest code iteration.
It's just a cleanup run.
Right. It does a syntax sweep to smooth out any of those weird deviations and ensure the code is clean and structurally sound.
Okay, I understand the mechanism now, and it really sounds incredibly futuristic. But I am still hung up on the comparison to the current standard.
What's the holdup?
Why is this mental simulation actually better than a real error log? If the CodeSim framework runs a test and gets a factual, mathematically accurate error log from a real compiler, shouldn't that hard data always beat an AI just imagining the execution?
You would naturally assume that real-world data is superior. I mean, it's a logical assumption.
Yeah.
But that assumption ignores the psychology of how large language models actually process information. The paper includes a specific case study that perfectly illustrates why hard data can actually break a model's brain.
Really?
Yeah, the researchers looked at how both methods handled a notoriously difficult, math-heavy programming puzzle. It's known as ARC-195E in the dataset.
Okay, lay it out for us. What happens when the traditional method hits a wall?
When the CodeSim framework tackles this brutal math problem, it runs the code against a public test case in the sandbox, and the code fails.
Standard so far.
The compiler feeds back a massive error log. We are talking about huge integers, complex modular arithmetic, just a giant wall of chaotic data. And because the prompt now explicitly contains the phrase error, output incorrect, a fascinating psychological shift happens within the model.
Does it get biased by the negative feedback?
It gets completely overwhelmed. The model starts trying to trace the steps in the massive error log, but the cognitive load is just too high.
Oh, I see.
The presence of the explicit error signal acts like a shortcut. The model essentially gives up, abandons its step-by-step tracing, and lazily concludes, well, the code is incorrect, without ever pinpointing the actual logical flaw.
It literally just sees the red text, panics like a junior developer on their first day, and says, yep, it's broken, I have no idea why.
Exactly. It relies on the explicit error signal instead of doing the hard work of reasoning. Now contrast that with how DryRUN operates on the exact same problem. DryRUN doesn't have a public test case to fail, so it never sees that massive, overwhelming error log. It is forced to invent its own input to test the code. And because it knows it has to mentally trace whatever input it invents, it naturally self-calibrates.
Self-calibrates how? What kind of input does it invent?
It inherently avoids creating inputs that are too massive for it to mentally process. Instead of generating arrays with thousands of huge integers, DryRUN chooses small, manageable, but non-trivial inputs.
Like what?
It picks something like n equals 5 and q equals 4. It builds a test case that is mathematically complex enough to test the core logic, but small enough that it can hold all the variables in its contextual memory. And then it traces the arithmetic step by step to actually find the real bug.
Okay, I love this. To synthesize this into a real-world scenario,
I love you too.
CodeSim gets handed a massive, convoluted corporate spreadsheet with 10,000 rows of data. It runs a macro, it breaks, and the AI is so overwhelmed by the sheer volume of numbers that it just throws its hands up and says, it's broken. But DryRUN, because it's working completely independently, decides to build its own mini spreadsheet. It uses just 5 rows of data, which it can easily wrap its head around, and uses that mini spreadsheet to perfectly debug the broken formula.
That analogy is spot on. By forcing the model to rely entirely on its own intrinsic capacity, the framework forces it to self-regulate. It stays within the bounds of what it can actually comprehend.
Which is so smart.
And that leads to productive, stable debugging, rather than just throwing spaghetti at the wall and guessing based on massive error logs.
The psychological aspect of the model self-regulating is fascinating, and the theory makes a ton of sense. But in a real-world server farm, We have to look at the scoreboard.
Right, the data.
Does the zero-example method actually outcode the traditional sandbox-heavy method?
The results are what make this paper a state-of-the-art contender. To ensure the evaluation was absolutely fair, the researchers tested the models on the live code bench dataset, but they specifically filtered for problems that were published after March 2025.
Ah, I see why that matters. If they used older problems, the models might have already seen the answers during their initial training.
Exactly, it prevents data contamination. We want to test their reasoning, not their memory.
Right.
They ran this gauntlet using frontier models like GPT-5 Mini and Gemini 3 Flash. And despite operating completely in the dark, with zero public examples to look at and zero execution feedback, DryRUN matched the performance of CodeSim.
Really? Matched it?
Yes. For instance, using GPT-5 Money, DryRUN scored an overall 67.5% success rate, compared to CodeSim's 64.2%.
So it actually outperformed the traditional methods slightly, even without the answer key.
While statistically, the margins fall within overlapping standard deviations, so we consider it a match in overall capability.
Fair enough.
But achieving parity while being completely deprived of the crutch proves a massive point.
Yeah.
The fundamental reliance on human-authored public tests is entirely unnecessary for frontier models.
Which brings us to the operational reality of this, because we have to talk about token efficiency.
Always comes down to cost.
It does. Anyone who has paid an API bill for an LLM knows that computing power is not free. The paper notes a staggering difference in cost. DryRUN consumes about 28,500 tokens per problem, but CodeSim burns through nearly 41,000 tokens. Why is the traditional method so much more expensive?
It comes down to the cascading effect of how these frameworks handle failure. CodeSim's default configuration is highly reactive. It allows up to 5 simulation loops for planning and another 5 loops for code repair.
Oh, wow.
For a difficult problem, the framework might run up to 25 nested simulations.
Meaning the model is writing code, compiling it, failing, reading a massive error log, and rewriting the code 25 separate times for a single problem.
Yes, it burns through computational resources as it repeatedly hammers away at the sandbox. In contrast, DryRN is proactive but strictly bounded.
Right, the n=2 limit.
Exactly. It forces the model to think deeply during the initial planning and then strictly caps the mental simulation at 2 loops. It does significantly more with less by thinking carefully up front rather than just reacting to endless error logs.
So if you scale that up to an enterprise level, thousands of developers using an AI tool every day, switching to a DryRUN approach isn't just about making the AI smarter, it's about saving millions of dollars in compute costs because the AI isn't wasting tokens guessing and checking.
The efficiency gains are massive. But there is a very important caveat to all of this.
What's the catch?
The researchers proved this works on massive frontier models, but they also tested an open-weight small language model, specifically a 7 billion parameter model, Qwen 2.5 coder.
Let me guess. Without the sandbox to hold its hand, the small model completely fell apart.
It failed entirely. It couldn't pass any of the difficult problems. And the reason why reveals a lot about how these models scale. The smaller model fundamentally lacks the multi-step reasoning capacity required for abstract mental simulation.
What actually happens inside the small model when you try to force it to use the DryRUN framework?
When the researchers prompted the small model to just write a plan, explicitly telling it not to write code yet, the model simply couldn't inhibit its primary training reflex.
It just couldn't help itself.
It eagerly started writing buggy code anyway. It couldn't hold the complex instruction to simulate without executing. It proves that while frontier models have developed deep self-regulation and abstract mental tracing, there is still a massive reasoning gap for smaller models.
It is like trying to get a hyperactive kid to draw a blueprint for a treehouse. You give them the pencil and the paper, but they just drop it and immediately start nailing boards together chaotically because they lack the impulse control to plan.
That is exactly the bottleneck. So for the foreseeable future, DryRUN is a framework that truly requires the vast reasoning and context-holding capabilities of a massive large language model to function.
So bringing all of this back to you listening right now, if you've ever used an AI to write a script, or if you manage a team of software engineers relying on copilots, the big takeaway here is that we might be evaluating and trusting AI based on a completely flawed premise.
We really might be.
By spoon-feeding these models with human-authored test cases, we aren't preparing them for the unpredictable reality of your daily work. Real software engineering doesn't come with a ground truth answer key.
And that reality leaves us with a profound implication for the entire AI industry. The WSO2 paper, poses a lingering question in its final discussion.
Which is?
If providing these public test cases often leads to the overconfidence gap and actually hides the model's true autonomous capabilities, should we completely delete public test cases from all coding benchmarks moving forward?
It is a massive paradigm shift. Think about that the next time you are trying to guide an AI through a complex task. In our rush to build smarter, more capable systems, could giving them the answer key actually be the very thing holding them back? Something to mull over as you go about your day. Thanks for joining us on this deep dive.